Bingo.
All right, so look, I'll get started. So what I'm going to talk about today is mainly the 200-inch mirror support system, its history and function. There'll be a little bit of an overview of what mirror supports do and some of the more modern applications of mirror supports. And a little bit about myself. I'm a chief engineer for Palomar. I've been involved with Palomar on and off for about 10 years. Started in 2008 working on Palomar projects, and then I took a little break after about 5 years and worked at Cornell on a submillimeter project, building a submillimeter telescope development. Then I came back to Palomar, I think it was 2015 until now. So first, I guess a little bit about what mirror supports do. Why do we even need them? Because imagine if you had something to put your mirror on that was infinitely stiff and that it could withstand any kind of changes in gravity or thermal conditions, you wouldn't need anything complex like a mirror support system. You could just let the mirror rest on this flat plate. However, mirrors are flexible, and so are the mirror cells that they sit within. And even as massive as some of these large telescope mirrors and mirror cells are, they are very flexible, actually more flexible than the smaller kind of amateur astronomy telescope mirrors that you might see. And here's kind of give you a frame of reference for that. Here's a basic equation for deflection of a plate, and this comes from basic theory of plates and shells and structural mechanics. And when you look at this equation, one of the factors that you can use is kind of to determine the proportional stiffness of a plate is the radius cubed over the thickness, or radius to the fourth over the thickness squared. So if you were to just compare two different mirrors of very large difference in size, like the typical amateur telescope mirror, which would be about 12-inch diameter and 1.5-inch thick, if you take this relationship of radius to the fourth over thickness squared, you get around a 576 value. If you do the same for the dimensional parameters of the 200-inch mirror, you get about 277,000. So you can see, comparing these, the 200-inch mirror is almost 500 times more flexible than this smaller mirror. And if you're trying to hold sub-micron surface error, you really need something more distributed support system to support that mirror, to manage that flexibility. So here's some examples of mirror supports. Very basic mirror support, just 3 points of supporting axially and 3 points supporting radially. This would be probably one of the most basic mirror supports, and it probably would work okay for relatively small mirrors. As you get bigger and bigger, you need a more complex support system. Here's one that has 27 point support, and this is for a 32-inch diameter mirror. One thing you'll notice in these mirrors, the more complex mirror support systems, is they have this kind of linkage assembly, which is commonly called a Wiffle tree. And you'll see this is a very common element in almost all multi-point mirror support systems. And where it gets its origin actually is from an old a way that you would manage horse-drawn teams where you have multiple horses pulling a single load, and you want to somehow prevent one horse from, or multiple horses from taking much more load on one side than the other. And by using this, what's called a Wiffle tree arrangement, you can equalize those forces to a single point. It's kind of the same thing we're trying to do with a mirror support system, is it's providing that kinematic support that equalizes the differences in forces, especially as you get variations in gravity vector, as the telescope would be pointing different places in the sky. Here's an example of a kind of a modern telescope mirror support system. This is from the James Webb Space Telescope. You can see this is a fairly large mirror. There's a person standing there over it. It's 6.5 meters, and this is a segmented style mirror rather as opposed to the monolithic mirrors of like the 200-inch and some of the other like the LBT and I think the GMT is going to also use monolithic mirrors rather than these small segments. But one thing you'll notice on the back here, showing the back of one of the segments, they have these supports, and these supports have actuators that actually drive each segment independently in tip, tilt, and piston to provide a contiguous surface that meets the air requirements of this mirror. This mirror has a unique condition that it's going to be in space, so it's not going to see kind of this large gravity load that it would on a ground-based telescope, but it does have to it has to come from a packed condition when it gets launched in the spacecraft to an unfurled condition as you see it here, and it's not likely that in that deployed condition it's going to meet its air requirements right out of the box. So they have these actuators to constantly adjust to provide the mirror, to give the mirror figure its desired shape within the air requirements. And I'm guessing also there's going to be a lot of thermal variations that might have to be managed. It would also change the shape of the mirror. So this is one method, and this is used also on the Keck telescope, a similar kind of arrangement with the actuators to drive the segments. There's also the use of pneumatics. In the very most basic method, you could support a mirror on airbags, and that could do quite a good job if the mirror was stiff enough. But on some of these larger, newer mirrors, like this is for the LSST, the new up-and-coming telescope that's going to be commissioned in a few years. So it has an 8.4 meter primary tertiary combination. This mirror is quite flexible, and it has a very high density of pneumatic actuators to provide the support to the mirror. Because you're with a mirror that's this flexible, you need that kind of spatial resolution to get to deal with any localized deformations that have to be managed. The 200-inch you see here, this is the Hale telescope mirror, and you can see it without coating, and also in the optical lab that was on campus when they were doing the testing and figuring of this mirror. It's borosilicate glass, otherwise known as Pyrex, slightly over 200-inch diameter. It weighs about 14.5 tons. Pretty heavy for its size compared to modern mirrors. I don't know if you noticed, but that other mirror I showed on the previous slide, LSST, that mirror was about 18 tons, but it was just under double the size. So you can see this is quite massive. And the thickness varies from about 19 inches to 23 inches. And you'll notice that there's an arrangement of core outs that you can see through the mirror surface. The actual top layer of the mirror is probably about 4 inches thick before you reach one of these core outs. These core outs are, the triangular shaped ones are mainly there for weight reduction and also to keep these a kind of uniform thickness of section between the surface and these webs, so that the mirror could cool uniformly and not crack from residual stresses. These circular pockets, these are where the mirror supports are located, and those were bored in place. Probably, I believe they were cast in a rough shape, but then bored in a final condition. Here is an illustration. I'm sure most of you are familiar with the Russell Porter illustration drawings. Very good drawings, better than most CAD models that we can produce today. And the Russell Porter was very skilled at taking mechanical drawings and producing these beautiful illustrations. There's 36 of these assemblies. You can see a cross section here where you can see the upper part, the gimbal assembly, is inside the mirror pocket. And then this mechanism down below we call the compound lever assembly. You'll notice that this photograph, this compound lever assembly looks different than the one in the illustration, and it is. This was the original design. This is the newer design that's been in place since about 1948. There was some design changes, and I'll talk about that in a little while. There is a lot of bearings in these assemblies, about 39 ball bearing, roller bearing assemblies per support, a total of about 1,400 ball bearings. A little bit more about that shortly. Here, I'd like to explain a little bit about how the 200-inch mirror supports work. And here's a kind of a functional schematic. I think this is a nicely simplified view. I think Hal actually created this schematic, and I just annotated it. I think it was very useful. There's two basic types of load that have to be taken up by the mirror support. The radial forces, basically if the mirror is sitting pointing at zenith, you have the weight of the mirror that needs to be managed. So each one of these supports carries an axial force, which is opposing the gravity load. As the mirror starts to tip, due to telescope pointing, away from zenith, then you start creating a radial force, and that radial force also has to be managed. So there's a combination of radial and axial. The way the mirror support works is there's the bottom compound lever assembly has these weights that hang out on arms, and the length of the arm and going through this mechanism creates a force going up through the center of the support, and then that axial force gets transmitted to these flanges off on the side, and that loads the mirror. You see the reaction force here in this kind of crosshatch condition. All the purple loads are axial. The radial force is created by the entire mirror support assembly, and it will want to tip right or left depending if the telescope is pointing right or left in response to gravity, and it will create a torque or a moment that gets produced through this gimbal mechanism, which then applies radial loads to the sides of the mirror pocket. And so so at any time you can have a combination of axial and radial loads going through this assembly. The one thing that I'm not showing here is there's defining points also that are at play to keep the mirror in its nominal position. The mirror is actually kind of floating on these supports if everything's working correctly, but you do have to have at least 3 points that provide the axial definition, 3 points to define a plane. And you have to have something that keeps the mirror centered and keeps it laterally positioned. And that's done through the center hole of the mirror. There's 4 fixed members in the center hole that are temperature compensated to provide the lateral definition. So a little bit of history now. Things, the mechanism of the 200-inch mirror supports was really quite an ingenious mechanism, and considering it's completely mechanical and what it had to do, maintaining mirror surface to sub-micron level, it did a really good job. But there was a lot of analysis done in the early days of when the mirror was being tested on campus, where they found that it didn't do as good a job as they would have liked. And so some improvements were made along the way. One of the things that was found was that the mirror supports tended to put a moment into the mirror that as the mirror would be tipped away from zenith and closer to the horizon, the mirror had a tendency to want to become more concave or close up, thereby changing the shape of the parabola, and that changing image quality and shifting focus. They thought about ways to resolve that, but they were pretty well fixed with how they were applying the load to the mirror from the mirror supports, and it was something that would have been very difficult to modify at this level in the development. So they decided to add a feature to compensate for that. And if you ever see, there are other support mechanisms around the perimeter of the mirror, which are called squeeze levers. You see them here, that also work off of a gravity driven weight hanging off of a lever, and those put a load onto the side of the mirror that as you move more from zenith, more toward the horizon, the load from these levers will increase, as you see in this condition, thereby putting a higher squeezing load into the mirror and opening up the parabola. There was also around, this was during the time when the mirror supports were actually already on the mirror was already on the telescope, and the final figuring was being tested. They found that the mechanism that they had developed, this lower compound lever support mechanism, had too much inherent friction. In order to get the reliability and surface quality they needed this mirror support system to have friction that was on the order of 0.1% of the load that it's trying to apply. Each one of these mirror supports is, on average, they're different depending on where they're located, but each one of them is carrying about 1,000 pounds of load. And so the friction needs to be a really small component of that 1,000 pounds, only 0.1%. And they actually found that most of the time, the original design of this lever support mechanism was actually around 1 or 1.5%. So an order of magnitude higher than what they needed. So they went to work and decided they needed to redesign that assembly, and they did. And this is the basic design they came up with. And it was amazing that they did it so quickly. It was done like within a year. And at the cost, total cost was about $18,000 for the 36 assemblies, so only about $500 per assembly. Just kind of give you an idea. If you have to build things nowadays, you know that $500 doesn't go very far. Amazing that they could do so much with so little at that time. Another improvement was during the final figuring of the mirror. They found that there was this kind of a residual astigmatism that did not want to go away. And they had a choice. Should they polish it out, which would have been a significant amount of time, or add a corrector? And Bowen, as an experiment to try to remove the astigmatism, went to the hardware store and bought 4 of these fish scales, basically springs, the calibrated springs. And what they were doing was putting an opposing load in 4 different places that would null out the astigmatism. This kind of feature is commonly used in mirror support systems that maybe not spring scales, but other types of features. They typically call it a warping harness. But the basic concept of using these springs worked, and that's actually what's still in place today. Some people believe that if we were to replace them, it would be bad luck, and there's a lot of superstition regarding these things, even though I've been pretty keen at putting something more precise in at some time. But it's really not, they're working fairly well, and they're not causing any trouble, so it's one of these things of why should you bother with it? There was a major undertaking that happened around 1993. The mirror supports that are they sit in a position below the mirror. And as I think most of you are familiar that the mirror undergoes a vacuum during the illuminization process. The mirror has the mirror support vacuum, or the mirror vacuum chamber has two sections. The upper section that the mirror surface sees is a very high vacuum at something around 10 to the -6 torque. But the lower section also sees a vacuum, something maybe 10 to the -5. That low pressure, and when the grease of the old bearings are exposed to that over and over, eventually that vacuum will evaporate and or deplete the lubricant that's in that grease. And basically all you're left with after repeated exposure to that vacuum are the solids of the grease, which is basically like clay and maybe waxes. So the bearings over time started to really get sluggish and not move freely. And attempts were made to try to free them up by regular exercising of the mirror, but it had limited benefit. So Hal took the brave step at learning and studying how these mirror support systems work, how you would actually remove them from the telescope, how you would disassemble and reassemble and put it all back together and have it work again. And it was a major undertaking given that it hadn't been done before. And they did this work over a period of about 28 days and 3 separate engineering runs. And after the completion of this, I should mention also that there was some work to study of what kind of grease should be used that would not have the same problem of the original grease that would not evaporate during this illuminization event. So Hal did some research in conjunction with some feedback from NASA, who have mechanisms that have to operate in low vacuum-like space. They proposed the use of a low vapor pressure grease called brake coat, and that grease seemed to be sufficient to do the job, and it was installed in these new bearings. And the system worked pretty reliably and was stable for about until 2007, and then some troubles started. Around mid-2007, we started seeing some severe image distortions that would occur, and they would come and go intermittently without any real correlation to anything specific. And sometimes the issues could be cleared up by exercising the mirror support systems or by moving the telescope to different orientations. But here's an example of one of those images that would be seen. This was taken with Faro. And here you can see a similar corresponding phase map from what the deformable mirror would be trying to do to correct for that. And it couldn't correct for it because it exceeded the limits of what the deformable mirror stroke was. So this was quite a serious issue. Again, here's another example. This is from LFC, a focus loop in 2008. Also, you can see very extremely distorted images where, from what we can see, the biggest aberration is astigmatism. So we needed to figure out what was going on, and we decided to remove several, I think it was two of the mirror supports, try to do some forensic work and try to see what's going on here, where is this problem? We spent some time analyzing these assemblies. We had some engineering time to do it, and we found 3 main issues. The main folks involved in this were myself, Hal Petrie, and Keith Matthews. What we saw was the bearings showed some corrosion. This was interesting in that the bearings had just been replaced in 2000 or 1993, so we wouldn't have expected to see them corrode. But it turns out, after doing more study about the brake coat grease, is that its use in the space applications was mainly with stainless steel bearings. And we had in the 200-inch, we used carbon steel, chrome steel bearings. So this was kind of a unique application also, that it saw some environmental conditions that you typically wouldn't see in space applications. So we learned that this grease didn't have quite the corrosion resistance properties that we needed. It did not appear that that was a major problem functionally, but it was trouble brewing that we needed to deal with. The big problem that we found was this, what I would call a force short circuit, where there was a tooling pin that was part of the assembly that engaged with another slot in a part that was that was fixed inside the mirror, and this gimbal assembly would migrate such that this pin would make contact and actually bind the assembly, and basically any benefit you had of this mirror support trying to manage the force was short-circuited by this interference. And this could happen on one or multiple supports at the same time. And what that would do is basically over-constrain the mirror and thereby creating huge residual forces that the mirror couldn't resolve, and the astigmatisms that we would see were the result. We also found that some of the parts had started to kind of disassemble due to just the motion of the mirror over time, oscillating and causing screws to back out. So those assemblies that had that risk, we implemented some retention features that would more strongly keep the fasteners secure. So we started a complete refurbishment again, this time with the benefit of the knowledge that Hal had developed during the first refurbishment. We started in January, and we did it in a one-shot program that lasted about 5 weeks. We had the whole observatory involved. We set up like an assembly line around the mirror and took the assemblies out a few at a time, and did a complete refurbishment, replacing bearings with new grease that we had specified. And I should mention also that one thing that Hal had the foresight to do during the first refurbishment was to test a grease that he thought might also be a useful option, which was from Nye lubricant. And it turns out that that grease actually performed quite well. That was one of the mirror supports we analyzed. And so we actually had a 15-year experiment running on the mirror supports where the grease was already validated. And it made it a very easy decision to decide what was the replacement grease to use. So after we finished all this work and put the assemblies back in, we did some before and after tests. And here you can see a phase map from the AO system before the overhaul, where you see some really significant distortions in the mirror. Here it's showing a peak to valley surface error of about 4 microns. And then after the refurbishment, significantly better. The astigmatism is mostly gone. The big error term now we see is coma, which is mainly an alignment issue. And it suggested that we need to do a better job at alignment now that we've knocked down most of the astigmatism problems. So I think that Rick will go more into detail about that in the next talk. So this is all I have right now. Is there any questions that anybody might have?
Yeah.
Yeah, I have a question.
Sure.
This is Curtis. A piece of lore I picked up early in my time as a docent at Palomar is that the lubricant that they applied in 1993, that NASA lubricant, was also used on the antenna of the, which probe was it to Jupiter, where the antenna did not extend properly? And that you know, part of the problem that we had at Palomar was due to faults of the same lubricant that had been experienced on that antenna on the Jupiter mission. Is that true? Is that just noise? What is it?
I don't know if that's true. Hal may be able to comment. My only comment to that is these are two significantly different applications, and what might be a good application, good grease for one application may not be good for another. But, maybe Hal, do you have any knowledge about that?
That story is correct as far as I know.
Oh.
But we didn't know that at the time we made the selection of the grease. But it became apparent that NASA was having trouble with these mechanisms to unfold antennae on spacecraft. And it was traced back to likely the problem with that brake coat grease. And they no longer use that.
I have a question. The measurements that produce the phase maps that you're showing, how were those measurements made?
Rick will talk about that in the next talk. He's using the AO system, the adaptive optics.
I have a question. There was a line on one of the slides that indicated that further improvements in the mirror support system are still being made. Can you address that?
What I mentioned was that further improvements in probably alignment will be made because, as I mentioned, comas appear to be the biggest aberration remaining after the mirror support work. And Rick will talk about that in his next talk also.
Great.
Well, we had agreed to reserve time for questions at the end. I guess, Jeff, thank you very much. That was great. And if I could pass the floor now to Rick, I'm going to talk about the mirror. Rick?
All right. Hello, everybody. Let's see. Let me go to that. Everybody see that okay?
Yes, I think so.
Okay. Let me minimize. Shoot. It's going to be a distraction. There we go. All right. Thanks, Jeff. So, all right, let me just jump right into this. I'm going to be talking today about how the surface of the 200-inch both has been measured historically and how we're measuring it now. Before I jump right into that, I want to mention, well, first pay attention here to an image of the primary mirror. This is with it out of the telescope, having recently been illuminized in 2000. I believe this is 2006. There's my daughter. She's a young little girl there. And what you'll notice here is, as in the reflection, you'll see these curved, curved points from various things in the reflection. Shows that this is indeed a parabolic concave primary mirror. What that means, it's got a very shallow curve to it, such that every point on its surface reflects back to a tight focus at prime focus. So there are two aspects to the shape of the primary. The first aspect would be the grinding and the polishing of the glass itself. I'm not going to talk about that today. That could be an entire hour discussion, if not longer. So I'm going to resist talking about that, other than to say there was a design, parabolic design, a specification in terms of how to grind and polish the glass to get to that design. And they finished that in, I'm going to guess, around 1950 successfully, such that that parabolic shape was met to a very high order. And we're not going to talk about that today. What I am going to talk about is how do you maintain glass shape, the shape of the glass, as the telescope is moved around the sky. As Jeff pointed out, the mirror supports are designed to do that job. They don't do it perfectly. What's the impact of not being perfect? And that's what I'm going to show you today. I'll point your attention to this slide. I found this on the internet, and what was interesting about it, it happens to be an interferometric measurement of a 2-inch optic used in an instrument that I supported in its design and building at JPL, which was just completely coincident. The fact is, it's a parabolic reflector. And I just wanted to point out that in the slides I'm about to show you, they're all going to be color coded in a very similar way. And it's going to be a 2-dimensional map just like this. So the way these maps work is if you see green, green is perfection. That means no wavefront error. The parabolic curvature where you see the color green is perfection. Where you see red, that is a little too high. A little too high. Where you see blue, that's a depression, which is a little too low. In this particular slide, there is a 3-dimensional representation, which I won't show going forward, but it might give your eye a good example of what this looks like. This happens to be an astigmatic shape. I'll show a little more about that for those of you that might not understand what astigmatism is. What a good analogy of what astigmatism is a saddle shape or a potato chip, whereby you're sort of pinching along this direction and those 2 areas go low and these areas go high. To give you an idea of what would be acceptable, I've put this slide here that shows some diameters that you might be familiar with in terms of microns. So first thing I'll say is whenever surfaces get low or high on the 200-inch primary, if the peak to valley approaches about 1.5 to 2 microns, then we start to have a problem. I'll show the details of that as I go forward, but to give you an idea of what 1 micron is, first of all, the human hair is on the order of 50 to 100 microns. Red blood cell is 8 microns. A bacteria is 2 microns. And I discovered in a deeper analysis of this that E. coli is 1 micron. Fun fact, the coronavirus is about 0.04 to 0.1 microns, or 40 to 100 nanometers. So here's where I try to get a little cute, even though I don't have the capacity to do it. This is showing what might be an astigmatic map with E. coli. On the order of 1 micron would be low here and a 1 micron high here, such that the peak to valley is 2 microns. I would challenge you, if you were to stand on the side and look across the surface, there's no way that your eye would pick up 1 micron deviation on the surface of the primary. So the point is that the tools used to measure the surface shape are incredibly sensitive, historically so, and we'll talk about that in a minute. So before I get there, I want to mention that in simple optical systems, such as your eye or the 200-inch telescope, there is a pupil and there is an image plane. So at the 200-inch, the 200-inch mirror, M1, mirror 1, is by definition the pupil. Every point on the 200-inch mirror focuses the rays of light to the image plane. If you have an astigmatic mirror, and this slide here shows, for those of you who understand optics, this is 1 wave of air, whereby these edges here are pinched and low by 1 wave, and these are high. And what you get is, instead of a nice tight star, your star starts to elongate in a little cross. The polynomial representation of these airs happens to have an odd and an even function. And all that serves to do is rotate the astigmatic shape. In this case, for this particular polynomial set, it rotates them 45 degrees. That's not really important. It just means that the resulting image is not as tight as it needs to be. Astigmatism tends to come in the 200-inch because of the mirror supports not perfectly taking out all of the forces on the glass due to gravity as the telescope is moved around the sky. There is an acceptable level and an unacceptable level, and I'll show you that here in a minute. Another issue with our simple imaging system at the Hale telescope is something called coma, whereby you have a lobe that is low and another lobe that is high. And the resulting image then is splayed out. So instead of being a tight circle, the area rings are splayed out in one direction, depending on the orientation of however the coma appears. And the way you see coma is when this essentially is the collimation of the telescope. For those of you that are familiar with telescopes, you know that one of the first things you need to do is make sure your telescope is collimated. What that means is that the optical center of the primary mirror needs to be aligned with the secondary that contains the imaging plane. If it's not in alignment, if the secondary is displaced with respect to the optical center, you'll start to pick up a little bit of coma. A small displacement resulting in small coma is okay, but if your displacement starts to become too large, on the order of several millimeters or more, then this error becomes so large that your star then is spread out unacceptably in the image plane. By the way, something happened to me when I was 40. I noticed I started to lose the ability to read computer screens and documents. Fuzzy. What I learned when I went to the eye doctor is that my eyes had become astigmatic. So what that means, I guess, as we age, the elastic parts of your eye that are used to look at the far field or come in close become more brittle, and it starts to pinch the pupil, sort of like, I think it's whatever, it's not important. It pinches the pupil in a shape that looks a lot like this. And so the letters start to fuzz out in this way that makes it harder to read. So the way you solve that problem is you put a piece of glass in front of your eye that has the very same error but inverted, so that when the wavefront enters the glass, it is distorted in an astigmatic shape, but inverted to what your eye does. Then your eye takes that and then reverses the error such that what's delivered is then a perfect image. So that's just another example of astigmatism. This is a slide from my adaptive optics talk that I gave a few months ago. I won't spend too much time here, but I do want to introduce again the concept of the Hartman sensor. What this is a way to measure the surface shape, and our predecessors used the Hartman screen while they were polishing the glass from about 1940 to 1950. The way it works is you put this screen, and those of you who have been to the 200-inch have seen that on the east side of the North Pier, the Hartman screen rests. When they were to use it, they would take the screen, mount it at the top of the telescope. The hole goes around the prime focus cage, and the edge is attached to the edge of the tube. And then they'd point off and look at a bright star. As the starlight goes through the mask, the light is blocked in all the spots, in all the locations, except for the circular holes. And what that would create as the light reflected off the primary and then focused at the prime focus would be a grid of spots, indicated here by someone's drawing. This is just from some textbook. And what happens here is if your mirror is perfect, then what would happen is all of those spots would be arranged in a grid that were equidistant from each other. If your mirror is not perfect, then spots would be too close together or too far apart. Where they're perhaps too close together, that might mean the surface of the glass is too high, needing some further polishing. Where it's too far apart, the surface might be a little bit of a depression there. So what happened over a few years while the mirror was undergoing these tests, my understanding was it was a sequence of 3 days where you would put the mask in, image, take the photographic plate out, analyze it, and then go out and start polishing on the areas that were high in order to form a more perfect mirror. What you're trying to do is separate the spots that are too close together and bring the ones that are too far apart closer together. Anyway, that's the fundamental property of the Hartman screen. The Hartman screen was used as recently as 1990, perhaps even a little after that, in 1990, I did read a recent letter suggesting that a CCD was used for the first time rather than a photographic plate. But in fact, the Hartman screen was used all the way up through 1990 in order to measure the surface shape of the primary throughout that time. In 1996, some colleagues from UC, Barry Shannon and Mitch Troy, brought the Palomar alignment camera, which is a CCD that rather than using a mask at the top of the telescope, a large mask, instead, inside the CCD camera are an array of lenslets. Each lenslet, as indicated here, takes the incoming light and focuses it to a spot. The advantage of doing that is you don't lose any light. If you remember from the mask, all the light is blocked. The only light that is used is what's allowed to pass through the circle. When you build these lenses, and they can be made extremely small and put it in a CCD, none of the light is blocked. It all enters a lens and then is focused on a CCD, which images the spots. Again, if the wavefront is perfect, if your mirror is perfect, then the Shack-Hartman sensor at prime focus would deliver a series of images such that the spots were equidistant from each other. If your mirror was not perfect, then you would get spots like this. And what's nice about using a CCD is the data comes out, it's digital. And then a computer can be used. And these are actual representations. I think this is 1999 data. The 1996 data showed that astigmatism was reasonably small. In 1999, they were measuring astigmatism, and you can see this for sure is an astigmatic shape where the depression goes quite low. And the peak to valley here was approaching 1.5 to 2 microns. And so they were just starting to get a notification that the sensors might be starting, the supports might be starting to have a little bit of trouble. All right, so in 1999, the adaptive optics instrument at Palomar was delivered. And around 2004, the manager of the JPL project and I got together and started to figure out how can we use adaptive optics telemetry data to measure the surface of the primary mirror. First of all, the AO system, as you might remember from my talk a few months ago, the AO system wavefront sensor is a Shack-Hartman camera, very similar to what I showed in the slide previous. Here's a representation of it. This is the wavefront sensor that was used from about 2010, I believe, until just last year. Some 4 optics, which aren't interesting. The lenslets are here, there's 4 of them, and they're very, very, very tiny. I believe they're on the order of a 1/2 inch square. And in one of these, there are 4,096 lenses in that very tiny area. The spots then are transmitted to the CCD here. This is represented, this is the screen, this is the control screen, or the GUI, graphical user interface, of the AO system. And the imaging coming out of this CCD is actually shown here. If you were able to zoom in, you'd see each one of these white spots are indicated, but it's hard to see here because there's 4,096 of them and they butt up next to each other. So it looks like a single image, but in fact, each one of these white dots is one of the spots that I was talking about previously. The imaging of the Shack-Hartman looks all the way back out through the primary. So what you're looking at here, this is the light from a bright star. And you see the secondary cage here, and you see the telescope spiders here. So you're actually looking down on the primary mirror. So what we do with the adaptive optics data is in the morning the next day, we take what's called low order deformable mirror positions that are averaged over 60 seconds. In fact, we typically take 5-minute data sets, sometimes 10 minutes, and average them together in order to average out the seeing effects. If you were to watch this system in action, what you would see is a very fast-moving system to take out the seeing. If you average that over at least 60 seconds or longer, what you're left with is a persistent shape which is indicative of the primary mirror. And what we do, in fact, you can kind of see it here. There's a little bit of a astigmatism action happening. That's actually probably atmospheric, but if you were to average this over 60 seconds, then the shape of the primary mirror starts to fall out. And we do that. So the very next morning, we gather all the data. We subtract a reference image, which contains all of the errors that are within the instrument itself. Here's a cartoon drawing of what the adaptive optics instrument looks like. There are a few small errors in this system, and we don't want those to bleed into our analysis of the primary mirror. So we take a reference source of an internal source, call that the reference, we subtract it from our averages, and what we're left with is the surface of the primary mirror. And the original data set, I actually took myself from 2004 to about 2007. Then I left to JPL, came back to Palomar in 2017, and rebuilt the scripts to be more automated. So every morning after an adaptive optics night since around 2018, we gather the data and couple it with telescope pointing and all kinds of other telemetry. All right, so here's an example of what comes out of this data. These are raw images of what the mirror looks like. In other words, this is 5-minute averages over the space of an hour as the telescope is moved around the sky. The reference was subtracted, so we really are looking at the primary mirror here, but I'll point out, and I didn't notice this until after I made this slide, there are a few things that get cleaned up in post-processing that are unfortunately showing here. So you'll see these peak to valleys. Some of you who are paying attention, you'll notice this is close to 2 microns. That should be a problem. Well, it's not, because we're smart enough to know that these are adaptive optics artifacts. Some of these highs and lows are edge effects where the wavefront sensor is seeing poorly illuminated subapertures, and they're artificially high or low. And in post-processing, these are zeroed out. So the numbers I show you and some of the maps I'll show you later, those have been taken care of. The point I'm trying to make here is that we're saving the data, and you can see the astigmatism sort of moves around as the telescope moves. The very first, this happens to be January 11, one of the last nights before we went down to coronavirus was January 11 at the beginning of the year. Here, the telescope is about 2.5 hours pointed to the west. I always get the sign wrong. I think I got that right. Positive is west. So this is 2 hours west at -5 degrees declination. And every 5 minutes, we're just capturing data. All of a sudden here, the observer that night chose to move to 1 hour east and +25 declination. So you can see the mirror went from a pretty stiff astigmatic shape to something a little less so. So my point here is that the mirror is changing as you're moving around the sky. And I'll maybe say a little bit more about that in just a minute. All right, so what's the impact of that? Here's a representation of a perfect mirror. There's no wavefront error in this simulation here. What this results in is a very tight star whose encircled energy is the diffraction limit. And I've superimposed on this image a couple of circles for reference. The green circle is a conservative estimate of what the best seeing diameter would be at this wavelength, which is the G band, right at 500 nanometers, 0.5 microns. The blue circle represents the typical median G-band seeing at Palomar. And again, these are conservative. There can be some debate. These probably should be a little wider than this, but that's not important now. Let me show you what happens. This data was taken in December of 2015. Of all the 172 maps that were generated on this night, I pull out the worst astigmatic mirror. This had 174 nanometers, or 0.17 microns of astigmatism. That's this, you could see astigmatism there, with a peak to valley of about 1.3 microns, resulted in an image that's distorted. That's true, it is distorted. but it's well within the best G-band seeing disk. What this means is you'll never see it. No one with an imager at prime focus or CAS focus will see it when the mirror behaves this well. Even though it looks like it's bad, it's actually not. I also pull out the worst chromatic error in this data set of 172 maps for this particular night. The worst, oh, I'm sorry, here it is. It's 70 and 80 nanometers in quadrature, means it's probably close to about 0.1 microns. You see a chromatic tail here, but even in this case, it's well within the best seeing disk. So it just means that the mirror is performing well. We don't have to worry about it. We can move on to other things. All right, as Jeff pointed out, around 2004, 5, 6, especially through 2007, 8, and 9, it was obvious that there was significant problem with the primary. So the peak to valley wasn't 1 micron anymore. It started to become close to 4. And I will tell you that the low order deformable mirror stroke peak to valley is 4 microns. There's no stroke left. It's saturated. So all these actuators here have hit their lower limit. All the actuators in this red region has hit their higher limit. I will tell you, this is a 2006 image before I was smart enough to put a circle to indicate where the primary mirror is, but you can kind of make it out. What this means is that the error imposed by the sticking primary was even worse than 4 microns peak to valley. So what does that mean? It turns out the data from 2006 to 2008 or 9, whatever I have, is in an older format that I haven't taken the time to modify to work with my newer scripts. So I just created a simulation here to show you what it means. If I put astigmatism at 0.1 microns or 100 nanometers, just astigmatism, such that the peak to valley is 0.4, which should be pretty good. Sure enough, you could see the astigmatic elongation of the image plane well within the seeing disk. If I create an image which has about 5 microns peak to valley, I just force it to be really bad and look. Now, all of a sudden, this astigmatic shape is sticking out of the best seeing disk, even extruding beyond the median seeing disk. And this is what our observers were complaining about in 2007, 2008, is when they were observing, especially if the seeing was good, they had images that were quite bad. They were elongated, bean-shaped, all kinds of funky shapes. Okay, so again, and the very last slide, I'll show a history so you'll get a better appreciation of the work that Jeff, Hal, and Keith did. But I'm just going to show the next couple of slides before I finish is that in the morning, since 2000, I'll say 15, but in particular 2018, after every adaptive optics night, the data is saved automatically, processed, a little report is generated, and I get to look at the images every morning just to take a quick look. What does it look like? These plots are also generated that shows the error depending on the telescope hour angle, the error depending on the declination, the error depending on the zenith angle of the telescope. And what I can tell you is after looking at this for over 10 years, I guess it's getting closer to 20 years, when the telescope is moved randomly, which science observers typically do, it really is very difficult to try to create a model or to pull any sense out of the data. The way I describe it is the telescope and the mirror combination is like a hysteresis stick machine. It really is very difficult to try to get a sense of when are you going to get a certain type of astigmatism where. If you could model this effectively, you can imagine a scenario where you could have an automated mirror support system that could take it out. But I'll say two things. One, no, unfortunately, this system has too much hysteresis, very difficult to predict. And two, I showed that as of 2012, 2010, the errors are so small that they are much smaller than the seeing disk. So there really isn't a great need to do that. The next to last thing I will tell you is that we tried a test, and I believe this was March or April of last year, 2019. We set the telescope at 2 hours east. We tracked on a bright star without moving to 2 hours west. So that shows this progression here. And what you see is now, for the first time I've ever seen, a very smooth transition of astigmatism. That's the first time I've seen that actually, if you were to let the telescope track very slowly from east to west, you could perhaps model out the performance of the mirror supports. Not that we need to do that, it's just that this could be a predictable machine, but of course the observers need to move all over the sky. We can't impose on them not to, and the error, it turns out, is very small, so it doesn't really matter. All right, this is my last slide. And what I want to show here is the progression of effort over the years and how it correlates with each other. So in December 1949 and 1950, the Hartman screen was used to measure what's called the 80% encircled energy. So if you take your star, a nice tight little circle, and you determine where 80% of the image of the flux lies and draw a circle, this is the diameter of that circle. The smaller the circle, the better. So in 1949 and 50, the average here, I have it written down, I think the average, it was about 0.68 arcseconds through 1949 and 1950. So the mean 80% encircled energy was 0.68 at that time. The alignment camera, Shack-Hartman data taken in 96 and 99, all of a sudden in 1999, that number jumps up. And this is when I think we're starting to see the first signs that the mirror supports might be starting to bind up a little bit. Astigmatism was 0.191 microns. Coma is a little higher than maybe you like. In 2006, 7, and 9, the adaptive optics method was used. And all of a sudden, these numbers really jump up. Astigmatism was very strong. Even coma was surprisingly much stronger here. This is indicative of an alignment error, and this is indicative of the supports not doing their job, as Jeff described in the talk prior. So in January and February of 2010, the work that Jeff described was done, and AO data and Shack-Hartman data was taken, and they're in reasonable agreement. The astigmatism had dropped, but coma was still very pronounced. In February and March of 2012, an effort was made to recollimate the secondary with respect to the primary when the prime focus was removed and then reinstalled for secondary reilluminization. And the results are fantastic. So since 2015 all the way to present, over almost 3,000 maps that we've got. A lot of data isn't presented here. There's a lot of data that's on disk that has been analyzed that's not presented in this table. But since 2015, we've got about 3,000 surface maps. And these are the average encircled energy, which now is, where do I have that number? It's a little lower. I don't have it written down. Anyway, so these numbers are slightly lower. Here's the plot of the sequence of data. If I tried to plot it with date, it makes it much harder to read. And so what I'm showing is a plotting of sequence here. This data is 1948, 1949 to 1950. The alignment camera and adaptive optics data shows when the astigmatism and coma were very high. And then this is the current data. And you might be able to believe that we're even a little bit better than our predecessors in 48 and 50. They probably, I'm not seeing enough of their data to make any strong conclusions there, but we're at least as good as when the mirror was delivered in 1950, if not slightly better. And here's the curve of astigmatism and coma, just showing the excellent work that Jeff, Hal, and Keith did with assistance from Palomar staff in 2010. Coma is the orange circles, so the alignment effort in 2012 was also very useful. And what we're doing now with adaptive optics data, and we're planning to resume here the first week of November. Once again, the data will be taken automatically the morning after the adaptive optics nights. There's on the order of 80 nights a year. We get that we get that data for free, which is piggyback on the observers who are using the adaptive optics system. So we don't have to call for an engineering night. We don't have to install this massive mask at the top of the telescope. We just get the data for free. And we're continuing to plot this data, look at it, report it. As soon as these numbers, if they start to creep up, hopefully we can intervene before it becomes such a problem that the rest of the community discovers it. And that's all I've got. Thank you very much. Hopefully I'm not too long here.
Rick, thank you. Thank you very much. Can we open the floor? Can we open the floor for questions?
I had a question. There seems to be a lot of emphasis on coma, and I don't know how you are distinguishing coma that's actually in the mirror figure from coma that's a result of the misalignment, but I wonder why you worry about it at all when you can just decenter an optic to compensate. The coma adds algebraically. So I guess the only thing I would really be concerned about as far as supporting the mirror is the astigmatism.
So, Jeff, do you want to comment on how difficult it might be to collimate this telescope?
Well, I think your question was why not displace the optics in order to address coma? Is that right?
Yes, that's right.
And that's actually what we did.
Great minds think alike.
That's how the coma was addressed, by properly aligning the secondaries to the primary, and making sure that the primary was pointed correctly to begin with, because over time things might have a tendency to migrate as people make adjustments, and you can kind of lose your reference, and I think that's what has happened over time.
Well, that's right. If you're decentering your secondary to compensate for coma, and the coma is moving around, you're going to chase it.
Well, the reason I wanted Jeff to comment is given the tools we have, and it's challenging to collimate this telescope. And whatever they did in 2012, and I don't have access, I haven't actually reached out to the folks who've done that. That's a very interesting question on what they did. But whatever they did the right thing. And that was independently verified, not just from surface maps, but by rotating. We put an imager at prime focus, I believe it was in April of last year, without a wind corrector, so that we would get chromatic images at the outer edges of the field. And then we took data there on a field. And then we rotated the camera 90 degrees and took data again, and used the tails of the coma to draw lines to the optical center in both data sets, and found an offset of something like 1.5 millimeters, which was nicely small. Comfortingly, happily, that matched almost exactly the amount of error you would expect that was being shown in the surface maps. So it independently verified that both methods were consistent, and that the resulting coma was very, very small. We have looked, Jeff and I and others, through the tools we have, and it's just really, it is challenging. It would take a fair amount of effort to build up the tools correctly in order to to have to do that effort again. And thankfully, if we just keep putting the secondary back in the exact same space, we should be okay.
Could I ask, if we've talked about the mirror and the mirror supports in terms of aging and refurbishment, the fundamental telescope structure itself with the trusses and so forth, is the material, the steel, in the same condition it was? I mean, I can see a possibility of getting a set or some kind of effect that would affect your collimation.
Yeah, I can't say that that there hasn't been some, I guess you would call, settling since the telescope was built. But I think at this point, given its long history, I'd say it's settled pretty well. And this telescope is so over-engineered from a structural standpoint that the forces that it's seeing are well within the elastic limits of the material. We're not seeing plastic deformation that would occur just due to the loading of it, the load that it has to carry. So I wouldn't expect to see that. And we are protecting the telescope pretty well from corrosion and the elements. So that would really be the only thing that would degrade it.
Jeff, this is Lynn. I have a question along those same lines. What about earthquakes? We didn't know as much then as we know now. Have there been any issues with seismic activity over the decades?
Hal, maybe you can answer that. Not within my tenure, but I know that after major events, there has been some inspection that was performed, and it didn't show anything significant from my knowledge. Do you know anything more, Hal?
I never had any direct experience with it, but I anecdotally heard from an associate of Jim Westfall's, who was on the observing floor during a big earthquake, that the whole structure seemed to shake in the wind and twist and bounce. And it's not inconceivable that that had some residual effects. But I have never heard of anybody tracking down what those effects were. It is worrisome. And when you walk in on the ground floor, you notice these big concrete pads with angled brackets of steel over the four corners of the base. That was put in by Serrurier to help keep the telescope from jumping off of its base. But again, I don't think it's ever been severe enough to bring them into active play.
So I have experience with earthquakes at the observatory. They've been small but close. And one, I think it was on the order of fourth magnitude within, I don't know, a few miles maybe. And what happened there was the slip clutch slipped and had to be reset. And that was the only impact that we could find at the time.
I might add one thing. The original mirror support system had an anti-rotation device built into it. And that was because they thought that if they were up near Polaris and slewed the telescope, that rotation of the telescope would cause the mirror to twist in a reaction. It was some years later, they realized that the system is really in full equilibrium, that the forces tending to rotate the mirror, the inertial forces, are exactly balanced by the mirror support system as well. So there is those anti-rotation devices, which were thought to add to the friction, were removed. And right now, I believe all we have is a small tether on one of the back supports with an associated load cell to take out any residual imbalance in rotation.
Yeah, that's right. And we found that was actually beneficial because some of the residual astigmatism we might have seen after the initial refurbishment in 2010, we were actually, some of the supports were contacting the cell walls adjacent to where they're mounted because the mirror was allowed to freely rotate. And by adding back that single tether to prevent mirror rotation, we eliminated that. And I can assume that there was some improvement from that, but I don't have direct before and after measurements.
Thank you. And good to see you, Hal.
You too, Lynn.
So I'm thinking about how we might put some of this information into our tours, if and when we ever have tours again. Would it be safe to say that in spite of the stickiness of the support mechanisms, there's no benefit to replacing them or doing anything more because the thing that limits us is the seeing? not the mechanisms. Is that correct?
Well, I believe that they're doing as well as they can do now from what their design intent was. We have good bearings. We have grease that's still not being depleted because it's a very low pressure grease. We've removed the issues that were causing the sticking. And so the system is working well. And could you get better with some type of a more modern active support? Yes, maybe a little, but as you mentioned, you'd never see the difference given the conditions.
Yeah. Okay.
Yeah, and I'd like to add the one thing I realize that I could have showed in the data set, something Jeff pointed to was the fish scales, which provides the astigmatic warping harness, effectively does that. If you take the average of the astigmatism error over all the sky, east, west, north, south, and average it, the number drives to 0. And what that means is that the fish scales are doing their job. It could be better, but I will tell you, and this is no joke, we've got about 300 things in our to-do list. And so then it becomes a question, do you want to spend resources on something that you'll never see?
Right.
If these things start to fail again, if something starts to go bad, who knows? In the future, maybe, I'm sure there's newer ways that we could either sense the load on some of these supports or other things, but I doubt it. I think Hal and Jeff and Keith identified the problem, did a fantastic job of addressing it. So we've probably got a lifetime, knock on wood, left and other problems to deal with.
Other questions? Other questions? Can I ask? There's a story that surfaces here every so often, particularly when we're illuminizing the mirror. The story is that borosilicate glass is water soluble, and that every time we wash the mirror, we are degrading the surface. This has come up a number. Is there anything to that?
I have no knowledge of that. And if it were true, it would be on a scale that probably, we'd have to study it on orders of thousands of years, not in our lifetime.
And that's the response I have heard when that issue has been raised.
Yeah, that change would be undetectable.
Rick, this is Alan. I don't recall you mentioning temperature changes. Can you, with the adaptive optics, watch the temperature, the shape of the mirror change during the course of a night?
We've gathered temperature data. I haven't seen any correlation with temperature change. I think just the fact that the astigmatism is so random. I'm not sure. I haven't tried. I'm not sure I could pull temperature out of it.
I think we do know that if temperature change is rapid, you're typically going to have a mirror that produces local seeing effects that can be quite significant, and that would dominate more than any kind of changes in the figure caused by that temperature.
And also, when you have big temperature changes, focus starts what I call screaming. It just starts moving very, very fast. Focus is not an aberration that we care about because, as you know, you can move the secondary with respect to the primary to take it out. And adaptive optics is measuring focus in real time and sending those corrections. So even if the temperature gradient is large, the AO system is keeping up with those changes. But other instruments don't have that luxury. So that's why we do things like put the windscreen up when it's colder inside than outside. We put the windscreen up to try to trap that cool air in so that we don't suffer from seeing effects and we can minimize the amount of focus change. If it's hotter inside, that's a problem that we have to live with. And anyway. But to answer your question, no, I have not. We saved the data. It's there historically, but I haven't looked in any detailed way.
Wouldn't it also be a temperature lag that you would be looking for? I mean, there's sort of a, I forget what the timing is, but is there a 8-hour lag or something between?
Yeah, the mirror
that
has
change?
a thermal time constant that's on the order of 24 hours. So there's only so fast you can force it to change because of its mass.
And if we know, if some weather event comes in and makes it, very cold outside and the mirror's hot, and so we'll turn the fans on. The fans under the cell, in the cell, and on the side of the primary, not so much to help that night, but knowing that the constant is on the order of 24 hours, perhaps we're helping the next night. So the fans help bring the glass to a more thermal equilibrium.
It's at the next frontier, I guess, if we were going to make a significant improvement in image quality at Palomar, is to look at the thermal environment of the entire dome. And we have some ideas on how to do that. Just, time and money is the only limitation, and our ambition, I guess.
Well, with that, we're almost an hour and a half into this, and Jeff and Rick, thank you very much. It's a great set of presentations.
Thank you.
And if there's nothing else present, I think we're about ready to close the meeting. Any other final questions? With that, I thank everybody for coming. I thought this was a great session. And in 2 weeks, Dr. Nadia Blagorovnova from Radboud University in the Netherlands will be speaking. Her topic will be the final dance, observing star mergers with the Hale telescope. So please join us 2 weeks from now, and thank you everybody. Thank you very much, and we'll see you then.
Thank you, Steve.
Thank you very
everybody.
much.
Thank you.
Bye-bye.